For most of human history, the universe spoke to us in only one language: light. Every star we saw, every galaxy we mapped, every explosion we recorded came from photons traveling across unimaginable distances to reach our eyes. But light is not the only messenger the universe sends. For centuries, we didn't realize it, but the cosmos has been communicating in multiple ways at once: through vibrations in spacetime, through invisible particles that pass straight through planets, through signals that don't glow, don't shine, and don't slow down. This is the story of multi-messenger astronomy, a revolution that changed how we observe the universe, not by looking harder, but by listening better. Imagine trying to understand a thunderstorm by watching lightning alone. You would see flashes of brilliance, but you'd miss the thunder, the rain, the wind, the full experience of the storm. That's exactly how astronomy worked for most of its history. Traditional astronomy relied almost entirely on light: visible light, radio waves, X-rays, gamma rays, different forms of the same messenger. Powerful, yes, but still incomplete. Because light can be blocked, it can be absorbed by dust, it can be scattered by gas, and sometimes the most violent events in the universe produce little or no light at all. For a long time, those events remained hidden. Then came a completely new way of sensing the cosmos: gravitational waves. Gravitational waves are not made of particles or light. They are ripples in space-time itself, produced when massive objects accelerate violently, like black holes colliding or neutron stars spiraling together. Einstein predicted their existence over a century ago, but even he doubted we would ever detect them. They are incredibly subtle. By the time a gravitational wave reaches Earth, it stretches and squeezes space by less than the width of an atomic nucleus. And yet, we learned how to feel them. When the first gravitational waves were detected, it was as if the universe suddenly gained a new voice, a deep physical vibration passing silently through our planet, unnoticed by our senses, but unmistakable to our instruments. For the first time, we weren't just seeing the universe, we were feeling it move. But gravitational waves alone could not tell the full story. They revealed that something massive had collided, but not always what it was made of or what happened afterward. To answer those questions, astronomers needed help from other messengers.
This is where particles enter the picture. Among the strangest of these messengers are neutrinos, nearly massless particles that rarely interact with anything at all. Trillions of neutrinos pass through your body every second. They come from the sun, from distant stars, from violent cosmic events, and you never notice a single one. That's what makes them so valuable. Because neutrinos pass straight through matter, they carry clean, undistorted information about their origins. They point directly back to the most extreme environments in the universe. Now imagine detecting light, gravitational waves, and neutrinos from the same cosmic event. Not years apart, not by coincidence, but together. This is multi-messenger astronomy in action. Its defining moment came when two neutron stars collided in a distant galaxy. First, gravitational waves arrived at Earth, signaling the final moments of a slow, catastrophic dance that had lasted millions of years. Seconds later, a burst of gamma rays lit up space. Then came visible light, infrared glow, and fading after images, captured by telescopes across the world. For the first time, humanity witnessed a single cosmic event through multiple messengers. And the universe told us something extraordinary. This collision created heavy elements: gold, platinum, and more, confirming that some of the atoms in your phone, your jewelry, even your body were forged in stellar catastrophes like this. What was once theoretical became observable. What was once speculation became evidence. This is why multi-messenger astronomy matters. Light alone can deceive. Dust can hide details. Distance can blur information. But gravitational waves ignore obstacles. Neutrinos ignore barriers. Each messenger compensates for the weaknesses of the others. Light shows structure and detail. Gravitational waves reveal motion and mass. Particles expose energy and direction. Together, they turn confusion into clarity. This new approach is transforming how we study black holes. When black holes merge, there is often no light at all, only darkness. But gravitational waves reveal their masses, their spins, and the moment space-time itself reshapes.
Add surrounding light or particle signals, and black holes stop being abstract monsters. They become measurable objects that influence galaxies and cosmic evolution. Multi-messenger astronomy is also solving the mystery of cosmic rays, particles so energetic that even our most powerful accelerators cannot replicate them.
By combining neutrino detections with light observations, astronomers can trace these particles back to active galaxies, powered by supermassive black holes. This is cosmic detective work, reconstructing events that happened millions or billions of years ago using signals that arrive on Earth today. And we are only at the beginning. Future detectors will be more sensitive, able to hear weaker signals from farther away. We will detect the mergers of supermassive black holes, events so powerful they reshape entire galaxies and send spacetime ripples lasting years. Multi-messenger astronomy may even help reveal the nature of dark matter, not by seeing it directly, but by catching the subtle signals it leaves behind. This revolution is not just technical, it is philosophical. The universe is no longer something we merely observe, it is something we listen to. Astronomy has become global and instantaneous. When one detector triggers, alerts spread across the planet. Telescopes pivot. Scientists respond in real time. The universe does not wait. This new way of observing challenges our assumptions. Events we once thought rare turn out to be common. Processes we thought impossible turn out to be routine. Multi-messenger astronomy reveals a universe that is violent, dynamic, and constantly active. It also humbles us. Many of the signals we now detect passed through Earth long before we had the technology to notice them. The universe has been speaking for billions of years. We just learned how to hear it. As our instruments improve, we will detect phenomena we cannot yet imagine. Just as radio astronomy once revealed a hidden universe, multi-messenger astronomy is opening entirely new windows onto reality. One day, we may detect signals from the first stars, or the collapse of the earliest black holes, or physics beyond our current understanding. And when that happens, it will not come from a single signal. It will come from many messengers arriving together, telling us something is different. This is how science advances, not through certainty, but through convergence. When light, gravity, and particles agree, the universe is speaking clearly. And when they don't, that disagreement points us toward deeper truth. Multi-messenger astronomy is not just a method, it is a reminder. Reality is complex, layered, and never fully revealed through a single perspective. Every new messenger adds depth. Every detection adds context.
From the collision of neutron stars to the whisper of space-time itself, the universe speaks in fragments. Multi-messenger astronomy is how we assemble those fragments. And as we learn to listen better, the universe does not become simpler. It becomes richer, louder, and more astonishing, revealing that it has always been speaking in more than one voice.